Okay, so we're back to the case. I will run the mesh. Okay, we have a perfect mesh. To stress that, look at that. In this case, the only problem that we have is skewness, and it's not a problem. It's just a small issue. 11 cells. You can visualize that. You have all your patches for the NCC. We're ready to run, and let's run the kinematics. Okay, so here you have this key, the discrete move mesh parallel. So it's going to run everything in parallel. It's going to save a lot of information. It's just doing the mesh motion. So remember, before doing this kind of simulations that since are into motion, first test the kinematics or the formation. When you are sure that it's working as it should be, move to the simulation stage. So like what we're doing with the meshing. So we have done steady body, MRF, and at this point we're super sure that everything works, and since you can see the scenes are relatively easy. So the meshing is running in background, and let me go back and remind you here, the script, run mesh, all your steps, then the NCC, this is critical step for the sliding meshes. Here we're moving in parallel, so look at that, we're moving so fast. Look at that, this stuff to use a different control date with larger times and so on. And how it's moving here. So remember that you go into constant, you're going to find this dynamic mesh. So see that this is move, and M means moving mesh. Select the region. Remember that you created that at meshing time, similar to the MRF. Here you select that region and then put it into motion, and that's it. Okay, so same stuff as MRF, you can use tables, no limitation. And assuming also that take your time, read the links, the links for OpenFOAM, because the boundary conditions, this is stuff I don't want to go into detail, but how to set up boundary conditions, NCC patches, and so on. So read that, but the case you have it ready to go. So the other file that I would like to open, so that is boundary conditions. Let me go to system. In system, you have the control dictionary, and N stands for moving mesh, and run is the one that I use for the solution. So nothing to mention here. I already mentioned this one, but look at that. Here you have the function object for checkMesh. Okay, you can use also checkMesh after moving the mesh to check the quality, but it's better to do it online. So what is happening here, running this and saving this all the steps as BTK. So look at that, it's still running, even for to do the mesh motion. It's a little bit time consuming. Okay, we have it 1 second here. If you read here, maybe you're going to regions, says it would say here fail 6 mesh checks. This doesn't mean that you cannot use the mesh. So this is probably, I don't know, developers are exaggerating a little bit there, or it's a matter of interpretation. Skewness is not a problem. Then this stuff, there are some other topological errors, some stuff that doesn't matter. If you're not happy with that, just all geometry, put it to false, and you're not going to see all those checks. You're going just to see the basic ones as checkMesh. But all that information of all these regions that they are failing and so on, all that stuff, if you go back in your folder, you see that now you have this BTK here. So if you open here BTK in this folder, you're going to see, okay, it's not that one, this is the one that I compute for mesh, sorry. You go to post-processing. In post-processing, remember that you have all the output of the function objects. You will have the output of the checkMesh. And for each time step, let me go 1, see that all those failed, or those steps that give you a warning, you have it there. So now you can open Parabio and visualize that. But the interesting one is this one, NCC coverage. This is the coverage of that NCC interpolation. So when you look at here, you're going to see visually you get that coverage. And look at that at this point in time 1, after 1 revolution, this is what we want, this 1-1. This is ideally what we want. And while running this one, you can check that coverage, everything, what is happening. Okay, you have it here, source, target, everything. And you can play different meshes, and you can check now that when they are very dissimilar, you're going to get very, very large errors there. So this is it. Now you check your mesh, and after you are happy, you can run. So let me go here as usual before. I'm not going to run the simulation, by the way. At this point we are ready. We have the mesh, as you can see, extremely easy. Even this geometry, that is not a simple geometry, but the power of having control in your geometry. See that when you know very well your geometry, you can do many things. We get a very good mesh, we put it into motion, and we're ready to run. So as I say, Snappy is a decent, don't use that option, it is in the slides. No, it's going to give you, with the NCC, it's going to give you an error. I was saying that Snappy, it is a decent measure. It's a good measure up to the point that you get the boundary layer. Then after the boundary layer, it can be tricky. LS processor, so I run in parallel. Okay. If you use Paraphone, it will work. No, talking about that ParaView with that NCC patch boundary condition, it will work, but you need to reconstruct. If you use Paraphone built-in, recall that the built-in, it will give you access to the decomposed case, but it's going to crash. And actually, well, let me show you how it's crashing. Apply, I'm reading the reconstruct, no problem. But when I put here decomposed case, look at the terminal. Okay, and okay, so it didn't give me the problem. Let me see the NCC. Okay, perfect. It didn't give me the problem. So sometimes it will crash. If it crash, for some reason, maybe I have an updated version, or is the Paraphone standard? Okay, we're okay to go. So let me close here. And let me put the propeller, the body. So these are the prop and body there. And let me go surface with edges, and let me go here. Edit, put it here, and there you go. We have this. See that inside you have your propeller. Let me put this view, and if I press here play, there you go. Your propeller is moving. You have all the interpolations here, so it's not showing. And this is it. Into motion, ready to go, fully and steady. It's a quartz mesh, but go ahead and use the finer mesh. Run the less simulation, and you can reproduce the same animation, the less that show at the beginning. And this is it. Very easy. Remember, you can put multiple bodies into motion. Remember the issues that the connection here, that the cylinder, this region, in some regions, you might have the collapsing and not perfectly matching. So finer meshes, you usually solve that. We also mentioned the trick about adding one inflation layer in this region just to force the non-orthogonality and to stress that I don't want to confuse you at a higher level or say that, okay, you need to add that. Actually, you need to add it, but it's, let's say, an extra trick that it might help you. And here, this one, I will want surface warframe, and okay, I need to enable. Let me enable internal mesh. Like this. Okay, surface with edges, and don't get lost with this ParaView. Okay, and there you go. So what I mentioned now, that this stuff here that sometimes is a good idea, like in the surface of the body of the airplane, now that this cell collapsing, you have some orthogonality issues now, so it is a good idea to enforce to have everything orthogonal now to the surface. So if you add one boundary layer, that it will help a lot. Doesn't need it, you don't need it, okay, it's not required, but as I mentioned, it's an extra touch, no fancy touch, but it can be done. And actually, if you press play here, look at that, what is happening. Okay, you have your interpolation. So basically now coming back now to that orthogonality. So here, look at that, cells are perfectly orthogonal to that interface, but now you have this issue collapsing. Might influence your interpolation, but not a big of a deal. So this is it. Now you have your mesh rotating. Hopefully things are clear, very clear. I'm quite sure that everything is very clear. And the next step will be running the simulation. So let me go back the scripts and run solver. That's it. So let me go, and I'm just going to run a few time steps to show you something that at this point you have everything. You have here in momentum transport, you have all the models, and actually I have it for the less enabled, so you can run the less simulation. We have many videos on Torrance modeling, so setting boundary conditions, you can follow that. But there you go. The simulation it is starting. Will give you always the quality of the NCC patches at the first step, then start to do its magic, and there you go. So we don't see here the output of the checkMesh because I disabled that function. I don't need it. That is something that you test a priori. When you're testing the kinematics, you test it. So this control run, so you go here, probably it is commented, or I didn't put it at all. Say actually, yeah, I didn't put it, but if you want, you can put it, and it's going to give you the quality of the mesh each time step, but you need it. You assuming that, I assume that you check everything a priori. So every time step you have all here, and look at that, as it is moving, it's improving a lot. It will change, and that's it. Now you have your simulation running, so it will be up to you. So at this point, I think we have covered a lot with this case. As I mentioned at the beginning, I can be here like it's meshing, and in this simple case I can spend a lot of time. Important to mention, so basically in this specific case, your final result should be something like that. This is with the fine mesh, or probably this is something much finer. I think this mesh is about 20 million. To mention that also the condition that I'm running, I think if I will recall, this is thrust. No, it's not the thrust producing. So here I have the propeller with a pitch angle of 10. If you keep running this one, it's not going to produce thrust, okay? You're not going to see the wake, but you should be able to reproduce the results. To remind you also that you have this Excel script. It's very important, okay, to estimate all cell size. So starting from your background mesh, according to refinement level. So if you choose 14, you know that at the surface you're going to get that refinement, or if you put there 8, you're going to get that refinement. So that is how you get your estimates, how you resolve well your geometry. You master your geometry, you know your dimensions. Now starting from background mesh, choose what features or how small you want to go. And then for the boundary layer, just choose the method. I recommend to use the final relative, give here this percentage, and then check here. And usually when you reach this target of 32, it's going to collapse. But then you can play around with your mesh quality parameters, change a little bit something here and there, and probably it's going to improve, but it's difficult to control. So usually the solution here is always you want to go 10 to the minus 5, much finer meshes. So to show you here, so if I go here 14, okay, so it's a refinement level of 14. You will be able, 14 is a lot by the way, so look at that 14, it will give you this cell size or edge size. Look at that, you arrive to this value. So usually these are the values that you are going to need for word resolved meshes in aircraft. So you will be about y plus 1 to their personal experience. Okay, so this is it. Okay, I hope you found this useful. Probably I mentioned that I want to prepare more videos, so probably, but it's on the geometry. So the important thing here is that we get these good results because already work in the geometry. So maybe I will show something in this geometry, getting the geometry in certain sections, but I think we cover all that. So with that being said, thank you, and hopefully I will see you in more interesting test case, probably the linear motion. I think that will be very interesting. In any case, if you have questions, you feel free to drop your comment in the comment section, and subscribe to help you create more training material and support the community. So thank you, see you next time, bye.